Okay, welcome back. We'll get started again with the next talk for our workshop. From another university with a very good optics program, I know. I spent many years there myself in Albuquerque. So we're happy to have Arash Mafi from the University of New Mexico. Tell us a little bit about that program there and some of the research there. He's going to talk about research and education in optics and photonics at the University of New Mexico, and then more on embracing disorder in optics. So
Thank you, Jason. All right, it's a pleasure to be back at the University of Arizona. Some of you may know I used to be a postdoc here. So you see the connections are all over the place. We all somehow are connected. And notice that Professor Goodman was talking about his students in here. And I consider myself the student of his students. So it's a pleasure to be here. And I know, am I between you guys and freedom or no? All right, I'll try to be entertaining as much as I can. So here is where I am, University of New Mexico. Look at the pretty picture of Albuquerque. So I like to take pictures all the time with my cell phone. So next 9 slides, I'm going to show you pictures of Albuquerque. So it's beautiful. This is what I see almost every day. It's in the street. Wild horses. Cactus and snow. Balloon fiesta, yeah? It's beautiful. It is. So I'm going to be talking about the research and education in optics and photonics at UNM, the Center for High Technology Material and OSE, Optical Science and Engineering program we have in there. And then I'll talk about the technical matters. First, I'll have a brief introduction into optics in random media. And then I will specialize more into the topic of Andersson localization. So this is where I work, Center for High Technology Materials. Our charge at that center is to promote a culture of research and education in photonics, microelectronics, and nanoscale materials and devices, and also application. In particular, I would like to focus on the interaction between UNM and federal laboratories, especially in there. We have Air Force Research Laboratory, Sandia, and Los Alamos. So UNM is a very, very special place if you have any visions of doing defense-related kind of work in the future. We constantly, our students go back and forth between these defense laboratories and the university. And of course, we have, as I will speak, we have programs that are geared towards building startups. So some of these numbers need to be updated. Right now, we have 17 tenure and tenure track faculty at that center. Our count of optics-related faculty at the University of New Mexico are 30-something. They are spread over different departments. Here, 17 are mostly optics/optical materials at this center. We have, these numbers are bigger now. We have 12 postdocs there and larger number of research faculty. We have technical staff and 75 grad students. Some undergrads also work in that place. We don't offer degrees. It's a research center. I'll speak to that later. And the way the center is set up, we have extensive modeling capabilities. We have materials growth and characterization. And also we do some fabrication work and device work. These are some of the areas that we have at our center. Our claim to fame is our center is home to 3 ERCs, engineering research centers. We are collaborators. We are not leaders in any, but these are the 3 engineering research centers that we are partner to. And only UC Berkeley has more with 6. So, and CMEM, which is the sister organization down the road, is involved in another ERC, Engineering Research Center. These are some of the, these degrees, 250 PhD and 313 master's degrees are the degrees awarded to graduate students based on their research at the Center for High Technology Materials so far in its 30-year lifetime. We have primarily, historically, has been electrical engineering. Our degree in optical sciences and engineering is taking over. We have a dedicated optics PhD and master's program. It's an interdisciplinary program between ECE and physics. And at any moment, we had approximately 70 graduate students enrolled in that program with 30-something faculty members in different departments. It's extensive collaboration. And we have people also working in chemistry and other areas. Our center and faculty is very multidisciplinary. In all these areas, including other areas of engineering, chemical and mechanical, we have faculty members working at that center. Approximate level of funding at our center is $8 million per year, which is very good for the number of faculty members that we have. Patents and startups and companies is a big deal for our center. This number now is 222 patents issued to that place. We, with our 17 faculty members, we hold 35% of the University of New Mexico's entire patent portfolio. And with that, also, our center generates has historically generated substantial revenue from primarily companies infringing our patents, and we're going after the companies and suing them. So economic impact of our center in Albuquerque and New Mexico is huge. Cumulative economic impact of our center right now is approximately $400 million. For every dollar that we have received from federal government and industry, we have given $2 back to the economy. So the numbers are in here. So our center was established with a $10 million money that was given to the state of New Mexico some 30 years ago. We have given, it's the only surviving one, Center of Excellence, and is given back handsomely to the state of New Mexico in terms of economic impact. We are in multiple buildings. The primary building that we have is a 60,000 square foot facility, including an extensive clean room, fabrication facilities. If you want to do semiconductor fabrication and growth, University of New Mexico is one of the primary places. If you want to do ultra-fast lasers, again, we have great people. These are some of the areas. I'll leave this slide for a few seconds so that you can see what areas we work on. So make sure you consider University of New Mexico also. Sorry for poaching team. All right. So now the technical part. So what I want to talk about is my whole life is about disorder. That's what I do, essentially, disorder and optics. So here is light propagation in turbid media. You see that all around you, say, for example, in clouds, or even those people who deal with light propagation in stellar environment. It's important. You look through this cloud and you don't see the plane, for example, that is flying above the cloud. So something happens to this light, and we want to understand how light interacts with the turbid media as it goes through. So here is another example. Light propagation in turbid media and optogenetics. What they do is, I understand my optogenetics colleagues, they put a fiber optics in this mouse's brain, and somehow they try to get the light to the places that they want to. There are other techniques, and light propagation matters a lot, how the light propagates through the brain, through the tissue. And this is another area that people are heavily involved and interested in understanding how light propagates in turbid media. You have very little control to custom design your material. The material is given to you by nature, and then you need to understand how you shoot the light and how you control it so that you get it to do what you want. This is another example of imaging through turbid media. So far, these examples that I am going through, it's more like you have the turbid media, you can't do anything about it. The disorder seems to be an impairment, and you want to try to address that issue and solve the problem. So disorder is bad, and we are trying to cure that. I'm going to switch gears later and come to stuff that disorder plays actually a good role. This experiment was done in 2012. This is by these guys. You have a scattering medium, very, very turbid medium, and you have an incident plane. And what happens is you see a speckle pattern in here. And then they try to use some optics and put a special light modulator to manipulate the phase or amplitude, or phase and amplitude of light. And here is just the phase, in order to get the light to focus in here. They put a detector to make sure that they get magnification in here. You see, it goes from speckle all the way to a focus point. And with this, essentially, they train the SLM so that you can image through the turbid media. So imaging through this is important. And there's a lot of work to understand if you have a very turbid medium, how would you see through it? And this is an effort that essentially they have done in order to train a spatial light modulator in order to do that. So these are samples of the work I'm going through of what's happening in the optics of disordered media. So of course you understand why they want to do that, because really the ultimate goal is to be able to image through tissue. Question is, can you optically see through the skull? Can you see part of the brain? Can you optically see that? And that is the effort that people are putting into imaging through the turbid media in order to see how far we can go with the optics in order to see through this turbid media. So there is a lot of effort. Now these are really, as I said, the turbid media is an impairment, and we are trying to solve some problems in there. Now sometimes it becomes beneficial. Let me give you an example of how you can use disorder in order to gain something, to benefit you. Some of you may or may not be familiar with the DBRs, distributed Bragg mirrors. Everybody knows that? Or is anybody here who doesn't know what a DBR is? What you have is a bunch of essentially optical layers of different refractive indexes. And what you do, you stack them right, and you can make great mirrors. These are perfect, almost lossless mirrors. The problem with this is that it's very bandwidth limited. So you get essentially here is an experiment that we did in-house with Professor Fizel. Essentially a stack of periodic material, dielectrics. These are the two refractive indices. You stack them up. And with 50 or 100 layers, you get essentially a perfect reflectance over a certain wavelength range, visible. Now, what happens if you make these layers random and disordered in thickness? So you have the same material, but you make the layers random and disordered in thickness. This is the reflection bandwidth that you get. Okay, some of you may have taken. So if you know Fourier optics, if you have randomness, if you create a white noise situation, you can access all the frequencies. Yeah. So if you stack up enough layers, then you get perfect reflectance over a very, very broad band. So this is the way to make extremely broadband mirrors, to make them disordered. So this publication and the work that we have done is going to come out soon in this area. There's other work in this area as well to acknowledge. Now, broadband mirrors happen in nature. Here is an example of a white beetle. What happens is the scales in a white, it's not colored or painted white or anything. What you have is a very small submicron structure that is very, very disordered. And this disorder acts like a very broadband reflector. So that's why white beetles look white. So here is another area where disorder in nature assists in doing the optics that we like to do. Some people use disorder in order to improve the solar cell efficiencies. If you want, in solar cells, for example, you have these silicon nanorods going from chirped square all the way to Penrose and quasi-random, all kinds of structures. You can actually vary the randomness and improve the absorption efficiency of light in a solar cell. So disorder is another area where solar cells, where disorder can help the optics. Sometimes you want to design some crazy optics. For example, you want super diffusion. You have light that diffuses through turbid media. Now all of a sudden you want, diffusion means a random walk process. Now, sometimes you may custom design your optics so that the diffusion turns into a super diffusion. You can design what they call the Levy glass, which simulates Levy flight. How do we know about these things? This is actually the pattern that a shark in the ocean, when the fish is scarce, that's how they hunt. Or pretty much all biological entities, they go through not a regular random walk process in order to hunt. When the food is scarce, they do these long jumps and they browse around the long jump. This is called the Levy flight. So people are interested in making Levy glasses in order to create super diffusion structures. So these are areas where disorder. So I changed this speckle because you suggested that it should become sparkle now. So we all know about the imaging using lasers. This is in honor of Professor Goodman. So if you do an image, if you try to construct an image with a laser, you're going to see the speckle. How do you do that? You make sure you kill the spatial coherence. One way to do that is to have the ground glass and essentially mess up the laser. Why don't you use LEDs or something else that is already messed up, or white light? Sometimes maybe you don't have the intensity in certain imaging applications, and you really want a laser, but you hate the spatial coherence of a laser. What would you do? You build a random laser, which is essentially, instead of having a nice amplifying medium with two mirrors, you create a structure that is heavily random, and you look at the spectrum. Instead of being a spectrum of a nice conventional laser, you get a very random spectrum. Here is an example of imaging with a traditional laser with all the speckles that will happen and gets washed out. Of course, this image is a bit exaggerated. And you image that you get with a random laser. Random lasers are great when you want low spatial or temporal coherence, and it's an evolving field. You make lasers, so they're not LEDs or anything. They're very powerful. You can even, I was going to show you later, are making them directional, but you lose the spatial coherence. That is an impairment for imaging application. So let's go to another area. Now I want to switch gears and go to the Andersson localization. So we are done with where you'd see samples of disorder in optics. Here is a very interesting phenomenon. It's called coherent backscattering. Pay very good attention. This is very, very interesting physical phenomenon. If you have a disordered scattering medium, and if you shoot light into this, let's have a plane wave hitting this thing. And light scatters back, of course, because there's disorder in there. And if you put a detector here, and if you collect light that is reflected as a function of the backscattering angle, all of a sudden you see that there is a huge peak right at the direction immediately that you shine light at 0 degrees. This is called coherent backscattering. And the reason for that is that you may think that when you shoot this light, and light is wave, a wave is defined by its amplitude and its phase. And you think that it goes through the scattering medium, and because of all this scattering, all the coherence and the phase is messed up, which is in a sense true. But if the scattering is elastic, and that happens to a large category of materials, some of the phase information is preserved in there. Combined with something called reciprocity in optics, together, that phase information gets carried out, and what will happen is you have these paths. If you go through a scattering path, there is always one that is reciprocal to that, and these paths happen to interfere constructively exactly at theta goes to 0. And what you see is a huge peak at coherent backscattering. And this is what is called a precursor to what we call Andersson localization. It's called weak localization. And you saw some of the work on Andersson localization, beautiful work by Professor Axel Scholzken in imaging through optical fibers. So I'll go through. So this is a precursor to what I'm going to call Andersson localization. And what you can imagine is if I put this medium in here and another one of this next door to it, you can create these closed paths and closed cavities that would create such random lasers for you, even if you don't have any mirrors. You just have a scattering medium. It just needs to be scattering enough. So the higher the scattering, the stronger the scattering, a better job will be done in here. So this work, actually, disorder in optics has landed 2 Nobel Prizes so far. And one of them I'm explaining in here to you guys is Andersson localization. It's based on this paper written in 1958. It's the most highly cited, not read paper. It's very difficult to read. It's very technical. So some people who work in this field, I ask them, have you actually completely read the paper? I say, oh, I've read half of it. So let me tell you what it is if you have an ordered array of atoms, the electronic wave function, for example, the way we learned, is a block periodic wave function that's spread over the entire material. But if this is disordered, the wave function collapses into small areas. This is called Andersson localization. There is the same analogy in optics. In optics, if you have a periodic system, you can have your wave spread over the entire system. You shoot a plane wave at a periodic system, it will emerge. At the right wavelength, it can emerge from the other side. But if you have a disordered system, things can get stuck. If you have a very turbid medium, if you have a source of light in the middle, shining, light will stay confined. It can. So here is an example of Andersson localization, but the 2D version. So here, just look at this material. Looks like an optical fiber. It's very long. What I do is I pick 2 materials, material N1, material N2, 2 different refractive indices, say 1 and 1.5. And what I do is I create a random pixelated situation where each pixel is approximately 1 micron by 1 micron, or half a micron by half a micron. And I randomly throw a dice. I decide whether it's N1 or N2, random, 50-50. And I create this thing. Now what I want to do is, here is what I claim. If I shoot my laser through this optical fiber, as the light wants to go through this, because it's a wave, it wants to diffract in the transverse direction. Because of the scattering in the transverse direction, it becomes Andersson localized. There is a stronger scattering, and it would just stay through and go through. So here is this simulation is the same size as, say, for example, this optical fiber. You put a little source in here. Initially wants to open up, but the scattering is so strong, it would go through. Now what happens is we have created an optical fiber where every point in the optical fiber becomes a waveguide, as opposed to having a core and having a cladding and the core only guiding light. Every point in an optical fiber becomes a waveguide. So let me tell you how we made this thing back in 2012. This is the very first attempt that we did, and some of this was discussed by Professor Scholzken. We took 2 species of polymers, polystyrene and PMMA, 40,000 from each. These are different refractive indices. This long each, and we mix them randomly. Here is the mixing process. It's extremely tedious. 80,000 pieces of fiber you have of 2 different species. You randomly mix them. Now, this, what I'm going to show you now, has turned into a commercial product. So a company is actually building this thing and is selling it, and this whole process is now automated. So, and then this whole thing was cast into a piece of glass like this and drawn into an optical fiber. So this is the cross section of the optical fiber. Of course, it's a polymer fiber. When you heat it, when you cut it, you have to heat it up so it bulges up. Otherwise, it's a perfect square. Approximately 250 micron by 250 micron. is twice the thickness of human hair. And if you etch away one of the polymers using alcohol or ethanol, you can see how this mixture, it's 20 micron by 20 micron approximately. You see that this random is really good. So this goes through. And as you follow, you see that the patterns stay the same, meaning along this optical fiber, you created a situation where along the optical fiber there is no variation, but transverse to the optical fiber you have a lot of randomness, 80,000 pixels. So this is the very first experiment that we did in 2012. We managed to we shoot light into this, and we move it around, and the optical this is what comes out. It's the same size as the optical fiber, and we moved this around, and this followed. And then here is the theoretical simulation and experiment in dB units against CCD camera. And agreement was very good to the noise of the CCD camera. And of course, what is good? Why do we want this thing? You can potentially have optical communications, spatial multiplexing, beam transport. We thought about imaging, nonlinear optics, and also random lasing. And essentially what I have done with my group and collaborators over the past 7-8 years is to tick off every one of these applications. We have managed to toy around with these structures and go through all these applications over the years. Here is our first attempts at beam multiplexing through these fibers. Is an imaging. This is approximately 60 micron. Now, of course, this is 2014, and you have seen, this got us a lot of publicity. So Physics World declared this a top 10 breakthrough. Comet landing was #1. So it was good for my group. We like that. And here is the first Andersson localization in glass. We managed to, this is with Clemson University. The way we did this, the way our Clemson collaborators did, was a piece of bubbly glass, really, really bad glass. And they pulled it really hard, and all those bubbles stretched. And then it becomes a transverse disordered material. So, of course, I have to acknowledge that Professor Scholzkin, who gave a talk, now they have taken this whole imaging through these optical fibers to the next level, and they are doing great work. We are not involved at the university. I'm not involved with imaging work. I do that with private companies now. We have recently shown the first random laser, directional random laser in these optical fibers. So what it is actually a beautiful random laser, but it's directional. It comes from the optical fiber. So it has all the properties that we have, but it's directional, so we can use it to do imaging. And most recently, we are doing four-wave mixing, and our goal is to have a tunable quantum entangled source of optical photons, or quantum correlated source of optical photons. The process is, if you have high power pump hitting a nonlinear optical fiber, you can generate, say for example green, you can generate a red and blue under the right circumstances through what is called a chi-3 nonlinear process. Essentially what you're doing at those two frequencies, you are amplifying the fluctuations, the 1/2 h bar omegas in vacuum. You're popping these photons out of vacuum. Now, these are the fibers that we are working with, drawn by Clemson University. And this result is going to come out in optics letters in the next week or so. This is the first observation of four-wave mixing. What you see, the red and blue, are these two lines. For those of you who know more, this is the Raman, 440 inverse centimeter Raman. So we are generating these. Now, this is good. The next step that we are going to be doing is we are going to be moving the pump around and essentially seeing these lines moving around and the correlation of the two photons moving around as well. And there is a lot of work also in our group on nonlinearity that we are pursuing. And with that, I conclude. Here is if you want to learn more about transverse Andersson localization, there is a tutorial that I wrote some time ago. It's in Advances in Optics and Photonics. issue 7, transverse Andersson localization of right. Those of you who use Mathematica, all the figures in the paper, there is a Mathematica script also for that figure. You can download all the Mathematica script and go through the tutorial and learn what Andersson localization and optics of disordered media is. And with that, I have to acknowledge my students and collaborators over the years who have worked on this project and Andersson localization. Of course, I have to acknowledge specifically Professor Axel Scholzkin, whom we have collaborated over the years from the University of Creole. He gave a talk already. And also Rafa. Where are you, Rafa? She works in my lab, an undergrad. So, all right, thank you.